So for a circle, what will be the electric field at the center? So if a ring is uniformly
Zero.
charged, correct. The ring is uniformly charged, then the center will have 0 answer. Correct. Okay. Now, if I want to find the electric field, okay, that will hold it.
So are you speaking now?
Oh, no, no. So now imagine we have a ring. Now I'm speaking. Audible?
Yes, sir.
So now I have a ring in which I remove a very small part of it. So let's say I remove a part which is very small. Let's call it the DL in terms of length. Or this, let's call it this as L. But L is very, very smaller than the radius. That's what we have.
Okay, sir.
The same charge is given, which is uniformly distributed, except that part is missing. So, so what is the electric field at the center? No, what is the answer?
Sir,
Yes.
sir, is it like KQ by R square by Q is like the capital, like the total charge of the body divided by 2 pi R into L?
Very good. Yeah, so the answer is correct. That's a K Q by 2 pi R into L, which is Q by R square. That's the right answer. This is 2 pi R. Okay.
Yes,
So
sir.
this is the electrical value. So now what we are going to do is, so now we have a ring and so we take a point which is at on the axial position and then normal to the plane of the ring. So from the center, if I go x distance away, I'll get a point P. So we are supposed to find the electric field at the point P. So definitely we cannot apply the formula directly, but we can understand or realize that every element taken on the ring will have the field and we can see the direction of a resultant field. So by taking the component and integrating within the suitable limit, we should be able to get the right answer. So can you try this question to find the E?
Yes.
Okay, go ahead.
Okay.
Yes, tell me.
So I'm getting the answer is KQX divided by R square plus X square whole power 3 by 2. So
Very good. That's the right answer. So now you can see this formula, and this is not just a formula. There is many things to uh, conclude. So if I put x equals to 0, then we are at the center, right?
yes, sir.
So at the center, the answer will be 0, right? That we
Yes, sir.
can get from this formula as well. Now, what happens if I go really far from this ring, like infinitely far? So if x tends to infinity, this will be again 0,
Yes, sir.
because the denominator is having the high power than the numerator, so it will grow faster and it will make it asymptotically 0, so it will tend to 0. So the whole idea is, if I plot the graph between electric field and the distance x, and if I take the center of the ring at the origin, and in fact you can draw the, so, so how the graph will look like?
So maybe like it reaches a peak and then again goes down.
Correct. So because the field is 0 at the beginning and 0 at the end, it means it must be somewhere reaching the peak value, and this value will again terminate to 0 asymptotically, something like this. And in fact, we can extend this graph on the other side, but we have to plot below the axis, because if I take a right as positive, then left will be negative. So the question is, at which point or at which value of x the peak will be achieved? That won't be a difficult task, because you can just differentiate the function and equate to 0. You should get the x value at which the peak is achieved. So can you find the x value by differentiating the function? Because it's a question of maxima and minima, right?
Yes, sir.
Yeah, try this out.
Okay. So I'm getting the answer is R by root 2, sir.
Very good. That's the right answer. So the the value of x which where this will be possible is r by root 2, and now this side you can say minus r.
Sir, I don't understand why it is like negative.
Oh, no, because you're getting x square equals to r by 2, no? This is.
No, sir, for like the blue color graph is negative, sir.
Okay, y graph is negative. Okay, so what we're doing is, if you are going on the left side of this ring, the electric field will have direction left only, no?
Yes, sir.
So at this point, what is the direction of electric field?
Sir, like left.
And at a point here, field is right.
Oh, okay, sir. Yes, sir.
So on one side we have the field towards right, on the other side we have field towards left. So we have two different directions. So if I choose the right as positive, then graphically I must plot left as negative. So that's the whole idea.
Okay, sir.
Yeah. So that is why we are plotting below it. But if you think numerically or value wise, then it is symmetrical graphs. You can just do like this.
Yes, sir.
But what we are doing is we are taking care of direction also in plotting the graph. So that is why it is drawn like this. Okay.
Okay, sir.
Yeah. Okay. So this is done. So once we have the formula for the ring, and if we are willing to find the formula for the disk, but we will do some more calculation here. So we'll talk about the point which is very close to the center, but not at the center. So if x is tending to 0, then electric field at center, or you can say in the vicinity of center, will be how much? AQX.
Yes, sir.
And now compared to r square and x square, x is negligible, so this will become r cube.
Yes, sir.
So this is the electric field at in the vicinity of center. And what is the benefit of this? I mean, why I'm writing this way? So if I choose a particle, so if we have a charged particle, let's call it a small q naught having mass small m, and if it is exactly at the center, the net force will be 0, right?
Yes, sir.
If the charged particle is at center, the net force is 0.
Yes, sir.
But what happens if you displace slightly and release? So if you displace, let's say this is minus q naught, so that we can have the attraction. So the moment you displace slightly, the ring will attract towards the center, isn't it?
Yes, sir.
So this restring force will let this charge to perform oscillation.
Yes, sir.
So if I make the ring fixed, and if the charge is displaced along the axis slightly and released, if a negative charge is displaced slightly from center, and released, if a negative charge is displaced slightly from center and released, then we find the time period of a small oscillation. Okay. So tell me. So the time period of oscillation will be how much? So you know the method, you find the acceleration, compare with the omega square x, and then write the time.
Okay.
So try this out, then I'll check. You need some help.
Yes. So,
Yes.
sir, I'm getting 2 pi under root of r cube m divided by k q q naught, sir.
Yeah. So let me just check. So the force will be simply Q naught into KQX by R cube, right?
Yes, sir.
And so the acceleration, so you can add acceleration is minus Q naught KQ X by M R cube, right?
Yes, sir.
Which you compare with omega square X, and you will get the omega square value, which is KQQ naught by MR cube, and the rest is 2 pi by MR cube by this answer, right?
Yes, sir.
Very good. It's the right answer. So we got the
Okay.
crux. So now we can do slightly more involved problem. So we have a ring. So what we have is we have a ring of radius r. So this rod is negatively charged with charge minus 2, and the length of rod is 2r. So, and it is kept in a gravity free space. The ring is fixed. So right now you can see that half of the rod is on the right and half is on the left. So the net force is how much? Net force is 0.
Yes.
Okay, because the right will be repelled. I mean, right will be attracted left, and left will be attracted right, and therefore this is charged. Now, if I give a slight displacement, if I just push it slightly ahead, then the symmetricity will be disturbed because on the left we have r minus x because that's 2r. And on the right side we have r plus x. So now we have the left side is r minus x and right side is r plus x, the lengthwise. So the net force will change, isn't it?
Yes.
So can you find the net force after displacing x?
So can I just take my pouch and come, sir?
Yeah, yeah.
The pen and the ink is over. Sir, the ink in this pen.
Pardon?
Sir, instead of the ink in the pen, I said the pen and the ink.
Okay, okay, fine. Yes.
Sir, I'm getting a pretty complicated answer.
Yeah, but the x is small, no? So you can make a small smart work. So let me tell you what you can do. Just generally, I lose my like pen every time. I keep somewhere and then I forget. Just let me search for it. Okay, got it. So the moment you displace slightly right, a part will vanish from this side and
Yes,
a part will appear here. So how much part will appear here?
sir. X will vanish and X will appear.
Yeah, so this is r minus x, this is r plus x, right?
Yes, sir.
Now, if I remove the r minus x from this side also, how much we're left with?
Yes, sir.
Which means the part on the left and right will cancel the force, this part.
Oh, yes, sir.
So the only force I need to calculate is on this part.
Yes, sir.
And that I will assume at a distance r minus x from the center. That's it. Because x is really small, so this is as good as saying that the length of the charge which will experience the force is only 2x at a distance r. That's it. So how to write the force? So force on a charged particle at a distance r from the center, because r minus x is really small. So the charge q is spread over 2r. So charge on the length 2x will be, let's call it, and this turns out to be qx by r. Okay.
Yes, sir.
And then now when it comes to force, so we can find the electric field at a location r minus x is k q r minus x, because that's the location, upon x square plus r square power 3 by 2, right? This is the formula.
Yes, sir.
And force will be equals to, because it's negative charge, we can write it as minus. So force will be q naught into e, right? This is the force.
Yes, sir.
Now x is very small compared to r, so we can in fact write as kqr by r square plus r square, which is 2r square power 3 by 2. Roughly we can write numerical value. And because we have to use so many approximations, so this is minus qx by r multiplied by, just right, this is the restraint force. So this is kqr upon 2 root 2 r cube. So acceleration will be minus kqq by 2 root 2 r cube into x by m, the mass of, mass of the rod. So which we can write as minus q. And the rest is same typical comparison. So omega square turns out to be k. Okay.
Yes.
Like this. So the trick was to cancel the equal length on both sides and only calculate the force on the extra length. That was the whole idea. Okay.
Yes.
So this is question number. All right. So this is answer. So the next question is from work energy theorem. So imagine if we have a uniform electric field in some random direction in a gravity free space, so if we have the uniform electric field in a gravity free space like this, and we have a ring, and this ring is uniformly charged. So this ring is uniformly charged, except there is a gap exactly at right angle. So this gap is at perpendicular, and this gap is very small. So the radius of this ring is r, mass of the ring is m, and the gap is very compared to r. So this L is very small, and the total charge is q is spread over the ring, and the ring is at rest in the gravity free space under the influence of uniform electric field. So question is find the maximum angular find the maximum angular velocity of ring. This will be like a nice practice for your rotational dynamics because that is what we have completed. So think for a while, then I will give you the required solution if required. So you have to think about the torque, and what you need to remember is that this is right now is perpendicular like this. So the on see everywhere the force will balance out, but this extra charge on the other side, which is equivalent of this empty space, will be the unbalanced force. So
Yes.
the the torque will be due to the force on this part only.
Sir, is Q by 2 pi LE is equal to I alpha the equation?
Yeah. So Q by 2 pi into R into L into R into sorry into E into R.
Yes.
So this torque is this much, but what will happen after some time when you will go from here to here, the torque will change because the force will be this much. No? So the torque about the center mass will be how much? It will decrease. So let's say it turns by theta. So you have to write in a general function of theta. And the torque will be zero only when this will come at this point, parallel to the field here. Then the force becomes like this. This is the maximum angular velocity will be at the instant when the force is parallel to the electric field. So the torque is now zero, right?
Yes, sir.
And if you go beyond this point, then it will decelerate. So because as theta will change, torque will change. So we have to write the torque as a function of theta. So this will be U dash E into R cos theta
Yes, sir.
equals to ICM, which is MR square, because it's this is a small one. Once again, so Q by 2 pi small r into L is the charge into E is the force into R cos theta is the torque in general, and the torque equals to I alpha. Alpha is
Emma, sir.
d omega by.
I. Yes, sir.
So I is how much here?
Emma square.
M R square, and we can write d omega as alpha is omega d omega by d theta. That's a better
Yes, sir.
because the function is theta, na? So now this is not doable.
Yes, sir.
Hmm. So when theta is zero, the omega was zero. When theta is pi by two, because the only angle will turn is pi. Let's say omega is omega. So this is sine theta from 0 to pi by 2, which is 1. The integration will give you 1. And this is omega square by 2. So you got the answer. Omega square equals to. So let me check the answer. This should be the answer. Yeah. Yes, this is the answer. So these are all questions which we solved from Pathfinder. It's to build up your understanding of electrostatic system. So electrostatics is a chapter which can involve every other chapter of mechanics. Okay, so that's the beauty of this chapter. So if you know this chapter, it means eventually you know all other chapters. Next. So this was the ring, and we solved many questions of a ring and its related mechanics problem that we can create. So the next question we can talk about is hmm, okay, something called equilibrium. Okay, so that next we come to electric field due to disk. So we can call it due to uniformly charged disk. So imagine we have the a disk which is something like this. So this is your disk, and let's say it is uniformly charged. So here, first of all, when I say disk, without any mention, the disk will be treated as this is non-conducting disk. And non-conducting disk means the charge is all over the thickness.
I don't understand the difference between conductors and insulators.
There's simple difference. Let's say when I say the word conductor, it means it will have the free charge carrier which we called electron. Okay, so I'll tell you in detail about the conductors and insulators. That's a complete topic for that is called capacitor. So no need to worry about that. We will go in great detail. Like we will see everything. We will understand everything about conductor. So conductor is a medium with a free charge carriers called electrons. Insulator cannot have the mobile charge carriers. It means every point or every charge which you distribute in the insulator, they are almost fixed at their respective location, but they can only make the local movement. So they can just shift slightly right or slightly left, something like that. So it is like there is a chair which is fixed to the ground. It's a plastic chair. You're sitting on the chair and you're like tied to the chair. So of course you can move your body a bit, but can you move thoroughly like from one place to the place? The answer is no, you cannot move. So you are like a charge which can make a slight right or slight left movement, but you cannot move across the length or dimension of the insulator. So that is called non-conducting sheet. But if we have conductor, then the electrons can actually go from one end of the conductor to another end, and which exactly happens in case of electric current. So current is nothing but the flow of those charges which goes from one end to the other end of the conductor. So conductor is a medium with infinitely, or you can say inexhaustible supply of free charge carried. That's the definition. And insulator, no zero free charge. They don't have any free charge. So when I give some charge to a disk, where the charge actually goes? The answer is this charge will only go this charge will only go in the thickness of this disk.
As the surface.
No, there's nothing like surface. So however thin you may think of, the charge will be part of the volume. Okay. So basically, if you look at the side view, let's say if I do the side view of the disk, so this is like a diameter part. The charge is everywhere. So when you give some charge, the charge is actually present in the volume. So that's called surface. Because thickness is very small. So we treat this as a sheet or like a surface. And the thickness is very small. Let's call it T. And the charge density is actually rho. So the total charge is how much? Density into volume, and volume can write as pi r square into T, right?
Yes.
But if you want to write in terms of sigma, which is the equivalent representation, then we have to write sigma into the visible area of the disk, which is simply pi r square. It's good to write rho 8, and then I can just so A is the visible area of disk. A is the visible. So these are two different representation. So the reality is sigma is the equivalent representation because they represent the same thing. So sigma is basically density into thickness. So that is how we equivalently express. So if we have a sheet with more thickness than the other sheet, then the sigma will be definitely more, having the rho equal in both cases. So rho is the reality. So surface is just a hypothetically assumed concept in every where throughout physics. The only reality is uh, the only
Density.
reality density, the volume. Volume density is the only thing. All other distribution is just equivalent way of representing. Understood?
Yes, sir.
So now let's say if I ask you what is the potential at the center. Center means somewhere here. So this is called the volume center. Now this is something more deep we need to understand. This is called volume center. But in most of the calculation, we talk about this point. and this is called center of surface. Which is just outside the disk. So if I ask the exact center, then the electric field will be 0. So E at volume center will be 0 because we have, this is a point of symmetricity. So we have half thickness on the left and half thickness on the right, and they will push each other, will make the net field 0, isn't it?
Yes, sir.
But if you are at the surface center, then we don't take inside, we take on the surface, and that's why this is non-zero. We can find the value very soon. Okay, so
Yes.
that is why to understand the second part, we need to derive something. So these diagrams will not be shown to you in the textbook normally. You have to imagine, okay, that whatever they mention, there is some thickness. So if I draw a disk like this, just for the sake of drawing, you can see there is a disk, and from the surface center of the disk at a distance x, so now we have a disk, and we would like to know the electric field at a point P, which is on the axial position at a distance x away. So definitely we don't have the formula, but we can make elementary ring out of disk, right?
Yes, sir.
And the ring formula we have already derived. So the way to solve is this simple. You have to first make the elementary ring at a distance r and dr thickness,
Yes, sir.
and use the formula of the use the ring formula as the elementary, and then integrate to get the answer. So can you do this question? Integration
Okay.
part? Yeah,
Yes.
try this. Yeah, try this. Okay, you got the answer?
Just a second. So,
Yes.
sir, for the elementary one, we just put kqx divided by r square plus x square whole power 3 by 2. And in q, we put q by r pi r square
Yeah,
into 2
okay,
pi r
okay.
dr only, right, sir?
Instead of q, you have to take sigma because answer I forgot to mention. The answer should be in terms of sigma. So you can convert the answer into sigma.
Sir, that means it's just sigma into 2 pi r dr.
Yeah, correct. So k sigma 2 pi r dr, and here r is the variable, right?
Yes, sir.
So kq x upon x square plus r square power 3 by. So now this is integrable
Yes,
from
sir.
limit
Sir,
0 to
so
etc.
here x square is constant, x is constant, so we just take it out, right, sir?
Well, why will take it out? You have to use the method of substitution, so you can take this entire thing as. So to
Okay.
solve this,
Yes, sir. Yes, sir.
you have to use the method of substitution.
Yes, sir.
Yeah.
So,
Yes.
sir, I'm getting 2k by sigma x into 1 by x minus 1 by x square plus r square.
Yeah, correct. So if you simplify, we get the answer 1 minus x upon x square plus r.
Yes, sir.
Well, this is the right answer. And now here we can play. So when we write x here, we take x from the surface center, not the volume center. And therefore, even if you put x equals to 0, so you are still outside the surface, just at the center. The E will be sigma by 2 epsilon. That's the answer when you are almost close to the surface. So this is the surface center, not the volume center. Okay. So now, if I take a situation in which when the disk becomes infinite disk, so due to infinitely large uniformly charged disk, so due to infinitely large uniformly charged disk, we have the disk which is uniformly charged. So the meaning is when the radius becomes infinite. So this is also called infinite shape. This is equivalent of infinite non-conducting uniformly so the formula says that if you look carefully, if you make r to be infinity, the second term will be again 0.
Yes, sir. So sigma by 2 epsilon.
Yeah, so it's the same answer, isn't it?
Yes, sir.
So it says something that if you are very close to a finite disk, if the proximity is if you are very close to the disk, then the disk will appear as infinite only, isn't it?
Yes, sir.
So that is the idea. Na? If someone is very close to the center, surface center, then, then for that point, the disk will appear as infinite, isn't it?
Yes, sir.
So although the disk is finite, but we talk about the infinity in terms of relative separation, and that is the reason the field will have the same formula as the center of the disk. So you can see both answers are same.
Yes, sir.
Okay. So that is what we need to remember due to the infinite disk. So now we can do some miscellaneous problem. So, so let's say uh, you have a disk in which this I remove a part of it and I remove it symmetrically. So this you can call as annular disk, and the charge is on this disk like this. So there are two ways to solve this question. One is you integrate by changing the limit. Earlier the limit was 0 to capital R. Now the limit will change. So if I give you the inner radius as A and outer radius as B, so if we have the inner radius A and outer radius B, so now if I ask you what is the electric field at a distance x at the point, so there are two methods. One is again you do the integration but change the limit from A to B. But the other is called principle of superposition, which simply says that here the small disk is missing. So let's first assume that it is present, and we know how to find the answer for the big disk. And then assuming we have only small disk, we can find the electric field, and the part which is missing we can subtract. So this is equivalent of a big disk and then you have the same point. Then you take a small disk and assume what will be the field at the same point. Now, because the small disk is absent and because their fields are in the same direction, so this will create a field like this, and if this will alone will create a field like this. So together, the net field will be how much? The difference of the two, right?
Yes.
So now you know what to be done. So can you find the answer? Net
Yes.
field. Yeah, try this.
So
Yeah.
I'm needing sigma x by 2 epsilon naught into 1 by under root x square plus a square minus 1 by under root x square plus b square.
Correct. So E will be sigma x by 2 epsilon naught, and then you will write as 1 upon x square plus a square minus b square, right? This is what you are getting.
Yes.
Very good.
So
So that's the
is
right.
this like pretty similar to like the negative mass concept?
Exactly. It is exactly the same what you thought. So that's the right way of thinking. So what we do is we deal with the negative mass concept. So we bring a negative charge concept. So we think that okay, we have a a plus layer and the minus layer coming together. So plus layer will create a big disk. We know the answer for the disk. The minus layer will create a small disk, but in opposite direction, and then we superimpose or simply add. So that's the right idea to proceed. So imagine if we have a situation like this.
Sir, can you just come back in a minute?
Yes. Yeah. So now you can see your question. So I am not showing infinite disk, but this is the infinite disk, and what we are doing is from the infinite disk, you're removing a small disk, which is finite. So these are same question. Like, just like instead of disk, I'm drawing a infinite sheet in a random
Yeah.
fashion. So it's infinite going in all directions, but that is how we generally represent the sheet. It looks nice. So the whole idea is, can you find the electric field at point P?
Okay.
Yeah.
So,
Yeah.
so I'm getting sigma by 2 epsilon naught into x by under root x square plus r square.
Correct. So that's the right answer. So the total field is sigma by 2 epsilon, and we have to subtract the disk formula, right?
Yes, sir.
So what you get is the absolutely right answer. Well, so after disk, you can do some question like this. So imagine we have a oh, I think I'm doing too much. A bit- So imagine we have a simply a hollow shell. So I'm removing the half part. So this is the hollow shell, and this is uniformly charged. So now we are supposed to find the net, and the sigma is given, net electric field at the center of curvature. So what to be done here is same thing. You can cut multiple thin slice of hollow sphere parallel to the base, which will behave as a ring, and we know the answer for the ring.
Sir,
So because
I'm able to hear
yeah,
you.
Audible now? Am I audible?
Yes.
Audible? Yeah. So you can see there is half sphere, half hemisphere. It's a hemisphere actually, and the hemisphere is uniformly charged. Okay. So we are supposed to find the net electric field at O, and the elementary you know how to take
So ring.
exactly. So ring, but the you have to take as theta to d theta. Right? You go theta from base and then cut d theta. Okay.
Oh, yes. So
Yeah, I'm audible.
yes, sir.
So
So you just started talking now, right, sir?
yeah, just I said I was quiet actually.
Oh,
So you got the answer?
sir, I'm getting sigma pi r cube divided by 8 epsilon naught, sir.
Sigma. Once again, sigma.
Pi r cube by 8 epsilon naught.
Okay, I think let me help you. Let's see this. Let me draw it bigger one.
Okay, sir.
I will remove the half first. So first of all, we have to move theta from the reference. So first you move theta, and then you make a small cut into theta. So if this is the r, this is the theta, this is the theta. So the ring is this, no? This is the ring. R. And from the center of the ring, if you look at the O point, the distance is how much?
Sir, r sine theta.
Correct. So first of all, we need to find the dq, the charge on this elementary circle, a ring. So the dq will be equal to how much? Sigma into the radius we have to take as 2 pi r cos theta,
Yes, sir.
and the
Into
width we
r
take
tan
as
theta.
very. The next step is writing the formula.
Yes, sir.
So the dE at O will be k dq. X is r cos sorry r sin theta, kq x upon x square plus r square. But if you look at the x square plus r square, that is nothing but the capital R square.
Yes, sir.
So
Alright.
our answer is simple.
Sir, I made a silly mistake there.
Okay, I got it. So you're making mistake here. No?
Yes, sir.
So this is now r cube, and then if you substitute the value of sigma 2 pi r square cos theta d theta. So everything, all r will cancel
Yes,
complete.
sir.
And 2 pi sigma k will be after 2 pi sigma k.
Sine.
The only
So
integration is
the sine also we can bring it out, right, sir? I mean not
ah,
sine, the two
yeah,
inside, sir.
correct. What you're saying is correct. Correct as k phi sigma sine 2 theta d theta.
Yes.
And now this is easy to integrate. And the limit will be from 0 to pi by 2.
Yes, sir.
Because at pi by 2, we will cover the entire hemisphere. So k we can write as 1 by 4 pi epsilon naught. Pi is pi, sigma is sigma. And the integration of sine 2 theta will be minus cos 2 theta by 2.
Yes.
And this will give you the answer 1. So if you do so, the final answer will be sigma by 4 epsilon naught. This is the famous answer. So later on, we will learn how to solve this in one line without doing the integration after learning the solid angle and the Gauss law. Okay. So we will learn about the Gauss law and solid angle, and then you can derive the answer. So this is the answer. Okay, what is left? So now we can, okay, for the sphere and the solid sphere and hollow sphere, we will derive the formula of electric field after learning the Gauss law. That's why that part I am not doing right now. Okay.
Yes.
So I think that we have covered the basic definition. Let me just see if I can add something. Mhm. Mm, uh, hmm. So we can do some more integration, one or two questions like this. So we know that again we'll go back to the, if we have a line charge, if we have an infinite line charge, and the lambda is the linear charge density. So what was the electric field at a distance r from the line charge, if you remember?
Sorry to record it, sir.
No problem. So the answer was 2k lambda by r,
Yes, sir.
which is as good as writing lambda by 2 pi epsilon naught r. So this is the answer. So now the line charge is very important. Okay. So now imagine if I give you a question like this. So now here we have a infinite sheet, but infinite lengthwise, but the widthwise it is finite. So you can see there's a finite width for the sheet, which is, let's call it a B, and the rest it is uniformly charged. So sigma is the surface charge density. Okay.
Yes.
So I choose a point here, which is in the plane of the sheet, but at a distance a away. And now I'm looking for electric field at point P. So think about it, how we can
Is
approach
it
it.
like along the plane of the sheet?
Yeah, yeah, it is along the plane of the sheet. So both are in the same plane. Okay.
Yes, sir.
So try this one.
Yes, sir. So will it
Yeah,
be, sir, like will the standard, like the line formula be integrated with limits b plus a
correct, correct.
to
A to A plus B.
a? Oh, yes, sir.
So you have to take one elementary thin part of the sheet which will act like a wire or like a line charge, and you know the formula for the line charge. So rest
Yes,
can do the integration. So you can simply cut a small part like this, and you can think of the distance from the point P to this point. This location is x because that's a variable. Write the formula in terms of x. This is a dx in length, and you have to derive the lambda from the thickness of the strip. What is lambda? Can you derive? How to relate the lambda with sigma? That's a trick.
sir, sigma by b is equal to lambda. Sir,
Sigma
sigma
by
by
b.
b into dx.
Uh, no. So what do you see? The rule is simple. You take a small part of the strip. So I have drawn a thin strip. You take a small part of it and try to write the answer in terms of sigma and lambda. The charge equate the charge value.
Yes, sir. So,
Yeah.
sir, I'm getting 2k sigma square by b ln of a plus b by a. So,
Sigma square should not come.
uh,
See, first of all, to understand the sigma and the lambda relation, we just take a patch like this of any length. Let's call it dl. So the charge on the patch will be how much? Sigma dl dx, right?
yes, sir.
That's a sigma into area. And in terms of lambda, we can write lambda dl only. Na? So if you compare the sigma into dx is lambda.
Yes, sir.
And we know the formula that dp equals to lambda by 2 pi epsilon naught x. And lambda we know is sigma dx by 2 pi epsilon naught x. So that's simple. So sigma by 2 pi epsilon naught dx by x, and the x will go from where to where? A to a plus b to cover the entire sheet. So the net field turns out to be ln a plus b upon a. Now tell me where you made the mistake in understanding sigma and lambda relation here.
Yes, sir.
So the rule is simple. Always try to take the elementary patch and try to relate the answer in two ways. Because what I said, even we can also relate in terms of density also by introducing thickness also. But that is not required. Now what I'm trying to say is, imagine if I let you know that there is some thickness also. In that case, you can also write the volume charge density. So let's say if I call the thickness as T. So it will go slightly deeper inside, right? Like this, like a cuboid. Now things will become really complex because in that case you have to write in terms of rho also.
Yes.
So just to demonstrate, I can write a density into volume, and volume will be the visible area into thickness. I'm just writing this. And this is equals to sigma into visible area. That's simple. So I can relate sigma as rho into thickness. That's always true. And just now I have related the rho dx as lambda. So lambda becomes rho t dx. Imagine so many complex solutions we can create. Understood? So although it is not required, but you should know that how to use the various relation to relate the lambda, sigma, and the last thing is rho. So these are always related. Just you need to figure it out how to do that. Understood? Only doubt.
Yes, sir.
Now you can also get a similar question, but slightly complex arrangement. So imagine we have a sheet. So now let's say we have an infinitely large seed. So the infinity is on this direction. So but the otherwise it is fine. So earlier we were finding the answer in the plane of the sheet, and now what we want is to find the answer, and not in the plane of the sheet, rather at a point P. And if I call the point P at okay, let's take some value. This is if I call x-axis, y-axis, this is z-axis. This is 0, 0, z. So z is the location. I'm just trying to find the answer. And and this is let's say given as 2a. A behind and A this side. And sigma is the surface under. So we are supposed to find the electric field at point P. So I will give this question as homework. So we will try at home. You can take half an hour, 1 hour, or whatever. Create and do your imagination, and you can make a simplified picture of this also to solve question. So there are a variety of things that you have to put effort into to get the solution, and I'll see the solution in the next lecture. Okay.
Okay.
And we'll start the concept of a solid angle and Gauss theorem in the next lecture. So next lecture will be Gauss law plus. So this will be the next lecture. Okay. Okay.
Yes.
So I have shared the resonance sheet with you.
Yes, sir.
Okay. So you can start solving. I mean, try to solve whatever you think you can. Okay.
Okay, sir.
Goodbye. Take care.
Thank you, sir. But sir,
And
just a second, sir.
yeah, I think I have shared all the PDF and video lecture, or something is remaining.
Sir, you have shared all the recordings, sir, till the
Okay,
last class. Sir, for me, the sigma, sir, once again, sir, the surface charge density and linear charge density relation. Can you just like point out what exactly I made mistake here?
Just a moment, you're saying
Sir, the relation between sigma and lambda, sir. I
okay.
tried away.
Yeah. So this
But
is
then
the strip. This is the
sir,
strip, right?
sir, I understood what you did, sir, but I don't understand what mistake I did.
So you need to send me your solution, then I can check. No?
Sir, now, sir, like if I tell you.
Yeah, tell me.
Oh,
So you can tell me, no, where you did the like what you see. Did you use the formula this one correctly?
sir, yes, sir.
So now this is the formula. So lambda we have to replace by this relation. So the mistake may be here. Can you check?
Yes, sir. There only I made mistakes.
Yeah. So that is the reason. So see, we are trying to find the sigma. Sorry, lambda only for this strip, not for the entire sheet. So we're trying to find the lambda of the strip, not of the sheet. If you write lambda of the sheet, then you can write sigma into B. Understood? If you want to write the entire sheet as a lambda, then we can write sigma into B, but that is not the case. So we are trying to write the lambda only for the strip which we have cut into the sheet. Okay.
Sir, I was more like dq is equal to sigma dA, sir.
Yeah, dq equals to sigma dA. And what is dA? So dA is dl into dx. Look at this is the strip. The thickness is dx
Yes, sir.
and the length is dA. So dq on the surface will be sigma into dl dx, correct?
Sir, for some reason I put uh the instead of dl I put sigma by d, sir. What does that give?
Okay. So you put sigma by db like this.
Yes, sir.
Uh, sigma itself is charge per unit area. Okay. Sigma
Yes,
is
sir.
itself. So if you think in terms of charge, then that will have some meanings. Q by b into dx may have the meaning of lambda, something like that. So that is for the that is also some sort of density, but sigma by b makes no sense actually here.
Yes, sir.
That is the mistake. So
Okay, sir.
and lambda into we put at dl only because we are trying to find the lambda this way. Na?
Yes.
Our length is along the sheet, so that is the dl. So lambda into dl, and by equating we are getting the relation, this relation.
Okay,
So
sir.
I'm going to share this sheet. You can look at it and you can find your other like error which you have made.
Yes, sir.
Okay, so fine.